This video accompanies the ECCV 2026 paper, Unwarping the Lens, a physics-grounded approach to video glasses removal, from Google Research and CTU Prague. The work addresses the removal of eyeglasses from video while preserving facial geometry, gaze, identity, and temporal consistency. Eyeglasses introduce both occlusion and optical distortion. Strong lenses can alter the apparent position and shape of the eyes, while reflections obscure additional detail. Generative inpainting and diffusion models can produce plausible restorations, but small variations between frames may change eye shape, gaze, or facial appearance. Existing approaches address different parts of this problem. General inpainting methods can follow image content but lack specialized facial and optical priors. Face-oriented generative methods may recover realistic details without maintaining temporal consistency. Video-to-video methods can reduce variation, but they do not explicitly invert the refraction produced by real lenses. This work transfers the photorealistic prior of a large generative model into a deterministic feed-forward restoration network. The generative model is used offline to construct training data. The resulting network is designed for efficient and temporally stable glasses removal in video. The first stage constructs matched synthetic examples. For each generated identity, a commercial generative model produces 13 poses and expressions, both with glasses and without glasses. Precise masks identify the lenses and frames. This creates multi-view and multi-expression pairs aligned at the level required for supervised restoration. Generated pairs are then filtered for structural agreement. Background and ocular L1 checks identify changes in pose and gaze, while a trained reconstruction proxy detects residual artifacts. After filtering, the dataset contains 1,860 identities, each represented across 13 poses with close structural and photometric correspondence. Generative synthesis alone covers only a limited range of real optical effects. To increase this range, the method estimates head pose and lens boundaries and constructs a two-surface lens model. Each pixel is traced through two applications of Snell refraction, producing a dense, physically derived warp field. HDR reflections are then composited with the refracted image. This augmentation converts each curated pair into multiple examples with varied lens properties. The training input combines generative appearance with simulated optics. The generated frame provides the eyeglass frame, surrounding face, and consistent illumination. Within the lens mask, the original content is replaced by the physically simulated refraction and reflection. The restoration network is trained to recover the corresponding clean face. The restoration model, JFSnet, combines semantic and local image information. Dino V2 supplies robust semantic features, and a convolutional decoder reconstructs fine facial detail. A direct skip connection also carries information from the input to the output, bypassing the latent bottleneck and preserving high-frequency details that do not require modification. Temporal stability is encouraged without optical flow or multi-frame propagation. During training, the model is constrained by translation-equivariance. A small translation of the input should produce the same translation in the output. This encourages restored facial features to remain attached to the moving head and reduces frame-to-frame flicker. Evaluation on the held-out FFHQ glasses subset includes 12,163 images. The method achieves an FID of 0.379 and a landmark error of 0.632. JFSnet processes video at 27.68 frames per second, supporting real-time application. A perceptual study compares the method with competing approaches along 5 axes: gaze preservation, temporal stability, removal quality, identity, and sharpness. Participants prefer the proposed method on all 5 measures. Qualitative evaluation on real CelebV text sequences also shows stable facial geometry under motion and effective correction of strong lens distortion. Comparisons with the baselines show fewer eye shape errors and less temporal flicker. This work combines generative synthesis, physics-based optical augmentation, and deterministic restoration for video glasses removal. The approach preserves identity and gaze while operating at real-time speed. The paper, project materials, implementation details, and additional results are available on the project page.